Okay, we are continuing chapter 16. We're looking at example 16.1, in which we are designing a steel beam. We had just, at the end of the last video, selected this as our steel beam, a W21 by 62, which has a plastic section modulus of 144. Now the thing we have to keep in mind is that by selecting that beam has a self-weight of 62 pounds per foot. That's going to cause additional load on the beam, and which is going to cause additional moment, which means we're going to possibly need a larger plastic section modulus. So with steel beams have a pretty good strength to weight ratio, so this is not often the case. But we can't just dismiss the self-weight. We do have to take that into consideration. So we need to find the additional moment caused by that self-weight. So that moment is WL squared over 8. So this time we're just looking at the self-weight. We've already calculated the plastic section modulus required for the externally applied load. This is just for the self-weight of the beam, which is 62 pounds per foot, multiplied by a length of 25 feet squared, and then we divide that by 8. And that is equal to, 4,800 and I'll round that up to 44. 4,844 pound feet. Okay, so I'm going to want to convert that to kip inches. So for every 1,000 pounds, there is 1 kip. And for every 1 foot, there are 12 inches. So if I take my 4,844 and I divide it by 1,000 and I multiply it by 12, that gives me an additional 58.1. I'll take it out to 3 significant figures. 58.1 kip inches. Okay, so if I plug that back into the plastic section modulus formula, so just due to the self-weight, this is just the self-weight by itself, I'm going to need an additional plastic section modulus of 58 kip inches. That's the additional moment caused by the self-weight, multiplied by the factor of safety of 1.67, divided by the yield stress of 50 KSI. So that is equal to 58 times 1.67 divided by 50 equals, it only equals 1.9. Even if I, let's say, round that up to 2 additional cubic inches of section modulus, if I add that, so the total required ZX would be the ZX I calculated earlier, 125.25, and let's say I add the 2 additional inches to the third required for the self-weight, that's now 127.25. Even if I rounded that up to say I need 128 inches to the third, that's still okay, because it's less than what is provided. Trying to draw a long arrow, it's a little hard to do. So if I point up here to the ZX I've actually provided by choosing a W21 by 62, that is still adequate. 144 is greater than 128. So as far as stress is concerned, it's good. even including the self-weight, the plastic section modulus is big enough that that it will not exceed the allowable stress. However, we are not done. We still need to check deflection, and we also need to check shear stress. So deflection is much more likely to control than shear stress. So that is the next thing we should do. We should calculate how much deflection is this beam going to experience, and how does that compare to what is allowed. Okay, so if we look at the problem statement, the problem statement says that deflection may not exceed the span length divided by 360. The span length was 25 feet. 25 feet is equal to 300 inches. So it's going to be 300 inches divided by 360. And 300 divided by 360 is 0.833. So 0.833 inches is how much we want to allow this beam to sag in the middle, to put it in simple terms. So that dimension there in the middle cannot exceed 0.833. If it does, then that's too much, and we're going to have to choose a beam with a larger moment of inertia. So moment of inertia, I sub x, is what really controls how much deflection. If you want a beam to deflect less, then choose a beam with a larger moment of inertia. So how much is this beam actually going to deflect? Well, again, we need to turn to Appendix H and look for the formula there for the maximum deflection for a simply supported beam with a uniformly distributed load. Okay, so I looked it up in Appendix H, and the maximum deflection that occurs at the center of a simply supported beam with a uniformly distributed load is 5 WL to the 4th over 384 EI. Okay, so I is what we want to know. We want to know how big our I value needs to be. So we can essentially take two different approaches here. We can either rearrange this formula so that it is, I'm going to write it up here, I equals 5 WL to the 4th over 384 E delta. Okay, we could do that and then just calculate how big does our I need to be, and then we can compare the I to the I value we have chosen, which I guess we haven't looked up yet, have we? So that's one thing we need to find out. We ended up choosing a W21 by 62. So that's what we have. We have a W21 by 62, and if we look up the I sub x value in the appendix, we look in Appendix A, we'll see that that value, actually we don't need to go to Appendix A, we can find that in the same appendix where we found our beam based on plastic section modulus, Appendix I. It lists both the plastic section modulus and the moment of inertia. And for a W21 by 62, that moment of inertia is 1330 inches to the 4th. So again, we can either rearrange the formula for I, solve for I, and then say, okay, is 1330 bigger than or less than the required I? The other way to go about it is to actually plug 1330 in for I and determine how much the beam is going to deflect. I typically like to do it this way. I like to solve for I, because if our beam does not have a big enough moment of inertia and it deflects too much, if we just plug the 1330 into here and we find that the deflection is too much, then we have to choose a stiffer beam, but we don't know how much stiffer it needs to be. We don't know how much bigger that I value needs to be. Whereas if we solve for I to begin with, this will tell us two things. It will tell us, is it okay? And if it's not, what I value should we choose in its place? So rather than calculating deflection, I'm going to calculate the moment of inertia that we're going to need. It's going to be 5WL to the fourth over 384 EI. Now, what is our W? Our W, as given to us in the problem statement, was 4 kips per foot. So we've got 4 kips per foot, but we also have the self-weight of our beam. Okay, the self-weight of the beam, because we chose a W21 by 62, is 62 pounds per foot. 62 pounds per foot, if I multiply that, convert it to kips, for every 1 kip there's 1,000 pounds. That's just dividing by 1,000, but moving in decimal place 1, 2, 3. So that's plus 0.062 kip per foot. So my total W is 4.062 kips per foot. But if I look in this equation, I've got E. The units for E are going to be in KSI. I've got I. That's going to be inches to the fourth. So it makes sense to go ahead and convert now these units, these linear units, to inches. So if I multiply my 4.062 kips per feet, for every 1 foot, there are 12 inches. And so I'm effectively going to be dividing by 12, and that's going to be 4.062 divided by 12, and that is equal to 0.3385 kips per inch. I'll need to do the same thing with the length. The length of the span was 25 feet. But I want to convert that. For every 1 foot, there are 12 inches. And so 25 times 12 is equal to 300 inches. I think I calculated that before. I should have remembered that. Okay, so I, the moment of inertia I value that we are going to need is going to be 5 times 0.3385 kips per inch. That's our distributed load. The length is 300 inches. That length gets taken to the 4th power. Don't forget the exponent. And then I'm going to divide that by 384 times E. E is the modulus of elasticity. We're talking about a steel beam here. All steel, according to the appendix in our textbook, has a modulus of elasticity of 30,000 KSI. And our delta value that we do not want to exceed, our maximum delta, is 0.833. So we can't go any bigger than 0.833 inches. So this will now tell us how much moment of inertia do we need so that that doesn't happen. So again, probably the most common mistake made here are units. So just do a quick double check. I've got kips, inches, inches, kips, inches, and inches. So everything should cancel out. All the kips cancel out with the kips, and the inches cancel out with inches. I don't have anything in feet. I don't have anything in pounds in this equation. So then I can just plug it into the calculator. 5 times 0.3385 times 300 to the 4th divided by 384 divided by 30,000 divided by 0.833 all equals 1,428.6. Let's say 14